This video will examine simple harmonic motion in dealing with oscillations and gravitation, focusing on simple harmonic motion dynamics and energy relationships, masses on springs, pendulums and other oscillations, Newton's law of gravity, and orbits of planets and satellites. First, let's define what simple harmonic motion is. Simple harmonic motion is the repetitive movement through an equilibrium position of an object that results in an equal displacement of the object from the equilibrium position on both sides. Objects that oscillate in simple harmonic motion include pendulums, springs, and guitar strings. Harmonic is derived from the fact that instruments, such as a guitar, produce vibrations that cause sound waves in the air. These vibrations are caused because of the simple harmonic motion oscillations, and they produce the waves that we call musical sounds. Now let's go through some important terms to know when dealing with simple harmonic motion. The period is the time it takes the system to complete one complete oscillation, and this is in seconds. A period is denoted by a T, usually. The amplitude is the maximum displacement of an oscillating system and is usually denoted by an A or an X. The frequency is the rate at which a system completes an oscillation and is usually denoted by a lowercase f, and its units are usually in hertz or oscillations per second. The equilibrium position is the point at which the system does not exert any force on the mass. This is where the mass will have its maximum velocity and its minimum potential spring energy. The restoring force is the force that causes the system to return to the equilibrium point, and this is the maximum restoring force is experienced at the maximum amplitude. Here we have some important formulas to know when dealing with simple harmonic motions. These formulas can also be found in the note sheet that's linked in the description of the video. The period is equal to 2 pi times the square root of the mass divided by the spring constant, and the frequency is 1 over the period. The period is also 1 over the frequency. They're inverse of each other, and the frequency is equal to the square root of the spring constant divided by the mass, and that's divided by 2 pi. The frequency is also described by the angular velocity divided by 2 pi, and the restoring force is equal to the negative spring constant times the distance of the object from the equilibrium position. Back and forth movement of oscillations can be described using cosine and sine functions such as the one depicted to the right. The cosine function is used to describe oscillations which begin at a displacement from the equilibrium point, and this displacement is usually the maximum amplitude. The sine function is used to describe oscillations which begin at the equilibrium point. When examining springs that move in simple harmonic motion, Hooke's law can be used to calculate the magnitude of the restoring force on the spring if there are no other forces acting upon the spring system. Hooke's law states that the restoring force is equal to the negative spring constant times the displacement of the mass from the equilibrium position of the spring. And this was introduced on the previous slide.
So, in this oscillation example, a spring stretches by 3.9 centimeters when a 10-gram mass is hung from it. If a 25-gram mass attached to the spring oscillates in simple harmonic motion, calculate the period of motion. So we're going to use Hooke's law, which is F equals kx. And since there's a force acting upon it, we're going to have mg equal kx. So we're going to have mass times gravity equals the spring constant times the displacement. And since we have mass, gravity, and the displacement, we're going to be able to calculate the spring constant. So we're going to have the spring constant equals mass times gravity over the displacement. And then the spring constant is going to equal 0.10 kilograms times 9.8 meters per second squared over 0.039 kilometers. And then from there, we calculate that the spring constant equals 2.57 newtons per meter. Now, in order to calculate the period, we could use 2 pi over the angular velocity, but since we don't have the angular velocity, we have to use another formula, which is 2 pi times the square root of mass over the spring constant. And we have the mass and we have the spring constant, so we're able to solve for the period. So we're going to have the period equals 2 pi times the square root of 0.025 kilograms over 2.57 newtons per meter. And then from there we calculate the period equals 0.63 seconds.
In simple harmonic motion, energy is transferred between potential spring energy and kinetic energy. If the spring is hanging, the potential gravitational energy is equal to the potential spring energy. The spring experiences a maximum kinetic energy and a minimum potential spring energy at the equilibrium point, and a maximum potential spring energy and a minimum kinetic energy at the maximum amplitude. The energy of a system moving in simple harmonic motion is equal to the kinetic energy plus the potential spring energy. The energy is equal to 1/2 of the spring constant times the amplitude squared, while the kinetic energy is equal to 1/2 of the mass of the object times the velocity squared, and the potential spring energy is equal to 1/2 of the spring constant times the displacement of the object from the equilibrium position squared. Simple harmonic motion also follows the laws of mechanics in that the non-conservative work is equal to the change in kinetic energy plus the change in potential energy.
So for our energy example, a ball is attached to a spring on a frictionless horizontal plane. If the spring constant is 12 newtons per meters and the mass of the spring is 3 kilograms, at what angular frequency will the system oscillate? So given is the spring constant, which is 12 newtons per meters, and the mass is 3 kilograms. And we're trying to find W. And W normally means angular velocity, but it could also mean angular frequency, because angular frequency is the magnitude of the vector quantity angular velocity. So in this particular example, W equals angular frequency. And so in order to solve for angular frequency, we're first going to solve for velocity. And so we're going to find the change in energy. We're going to find the change in kinetic energy and spring energy. And so we're going to have initial kinetic energy plus initial spring energy equals final kinetic energy plus final spring energy. And since there's no initial spring energy and no final kinetic energy, those both are going to equal 0. So we're left with initial kinetic energy equals final spring energy. So now we have 1/2 mv squared equals 1/2 kx squared. And since we're solving for velocity, we are going to end up with velocity equals square root of kx squared over m, which is velocity equals the square root of the spring constant times the distance squared over mass. And then we're gonna solve for the angular frequency, and we're going to use the equation velocity equals the angular frequency times the distance, and then we are going to solve for angular frequency. So we're going to have the angular frequency equals velocity over the distance, and then we are going to plug in the square root of kx squared over m as velocity. And so we're left with W equals the square root of kx squared over m over x. And then after simplifying, we are going to have that angular frequency equals the square root of 12 newtons per meter over 3 kilograms. And then we are going to solve for angular frequency, and in the angular frequency equals 2 radians per second.
The maximum velocity and maximum acceleration of an object moving in simple harmonic motion is experienced at the equilibrium point. The velocity and acceleration of the object can be derived from the position function of the object, which will either be a sine function if the object begins at an equilibrium point or a cosine function if the object begins at the maximum amplitude. Let's go over some important formulas to know when dealing with dynamics in simple harmonic motion. When looking at the position can be calculated by multiplying the amplitude times the cosine or sine of 2 pi times the time divided by the period of the oscillation. Whether you use cosine or sine here is dependent on whether the object starts at an amplitude or if it starts at the equilibrium position. The position can also be found by multiplying the amplitude times the cosine of the angular velocity times the time plus the phase constant of the object. And the phase constant describes a displacement that is not the maximum amplitude. The velocity can be found by multiplying the maximum velocity times the square root of 1 minus the displacement of the object divided by the amplitude of the object squared. It can also be derived from the position function, and so that would give us a velocity that is equal to the negative angular velocity times the amplitude times the sine of the angular velocity times time plus the phase constant. We can also find the maximum velocity by multiplying 2 pi times the maximum amplitude times the frequency, and this would be equal to the angular velocity times the amplitude, which we can also see from the velocity function is the maximum velocity, because once that sine of Wt plus the phase constant goes to 1, that'll be where we have our maximum velocity. The acceleration can also be derived from the position and velocity functions, and so the acceleration will be equal to the negative angular velocity squared times the maximum amplitude times the cosine of the angular velocity times time plus the phase constant. The angular velocity is equal to 2 pi times the frequency, and it is also equal to the square root of the spring constant divided by the mass of the object.
So, for the simple harmonic motion dynamics example, we have a 200-gram block connected to a light spring for which the force constant is 5 newtons per meters, and it's free to oscillate on a frictionless horizontal surface. The block is displaced 5 centimeters from equilibrium and is released from rest. Given is that the mass equals 0.2 kilograms, that the force acting upon it is 5 newtons per meters, and the displacement is 0.05 meters. And we are trying to find the period, the max speed of the block, and the max acceleration of the block. So first we're going to find the period. And so when trying to find the period, we are first going to solve for the angular velocity. And angular velocity is equal to the square root of the spring constant over mass. So we're going to have the angular velocity equals the square root of 5 newtons per meters over 0.2 kilograms. And then that leaves us with that the angular velocity equals 5 radians per second. And so to solve for the period, we use the equation, the period equals 2 pi over the angular velocity. So we use that the period equals 2 pi over 5 radians per second. And then we solve for period, and the period equals 1.26 seconds. And next we're going to solve for the max speed of the block. And so the max velocity equation is the max velocity equals the angular velocity times amplitude. And so our displacement equals the amplitude. So our amplitude equals 0.05 meters. And so we're going to have that the max velocity equals 5 radians per second times 0.05 meters, and then when we solve for the max velocity, we get that the max velocity equals 0.25 meters per second. And lastly, we're going to solve for the max acceleration. The max acceleration equation is the max acceleration equals angular velocity squared times amplitude. So we're going to have that the max acceleration equals 5 radians per second squared times 0.05 meters. And then from simplifying that, we are going to have that the max acceleration equals 0.25 meters per second squared.
A mass on a spring is oftentimes moving in simple harmonic motion. However, there are sometimes additional forces that you have to account for, such as a frictional force. This is a non-conservative force, and so you have to adjust your energy equation so that the work done by friction is equal to the change in kinetic energy plus the change in potential spring energy.
So, for our restoring force example, we have a stretched spring that supports a 0.1 Newton weight. Adding another 0.1 Newton weight, it stretches the string by an additional 3.5 centimeters. What is the spring constant of the spring? So we're going to use Hooke's law, F equals negative kx. But since the string is stretched, it negates the negative kx, so we're going to have a positive kx. Therefore, when we're solving for k, which is the spring constant, we are going to have k equals F over x. And so we're going to plug in 0.1 Newton for our force and 0.035 meters for our displacement. And then we're going to have that the spring constant equals 0.285 newtons per meters.
Let's move on to simple pendulums. A simple pendulum is defined to be a mass hanging from a string or rod with negligible mass, and its period and frequency are dependent on the length of the pendulum and the acceleration due to gravity. Simple pendulums only include pendulums that experience a radius of 15 degrees or less, because the difference between the radius and the sine of the angle is less than 1%. Simple pendulums experience a maximum gravitational potential energy and a minimum kinetic energy at the maximum amplitude, and a maximum kinetic energy and a minimum gravitational potential energy at the equilibrium point. Let's move on to some important formulas to know when dealing with simple pendulums. The period is equal to 2 pi times the square root of the length of the pendulum divided by the acceleration due to gravity, while the frequency, or 1 over the period, is equal to the square root of the acceleration due to gravity divided by the length of the pendulum, and that's divided by 2 pi. The restoring force on the pendulum is equal to the negative mass times the acceleration due to gravity times theta, and because the displacement of the object is equal to the theta divided by the length of the pendulum, and theta is equal to the displacement divided by the length of the pendulum. And so we can plug that into our force equation to find that the restoring force is equal to the negative mass times the acceleration due to gravity times the displacement divided by the length of the pendulum. And because the restoring force is equal to the restoring force from Hooke's law, or negative kx, we can find that that k, or the spring constant, is equal to the mass times the acceleration due to gravity divided by the length of the pendulum. Pendulums also follow the laws of mechanics, and so the non-conservative work is equal to the change in kinetic energy plus the change in potential energy.
So for our pendulum example, we have a mass of 0.5 kilograms that is hung from 2 identical springs of negligible mass. The mass causes each spring to stretch by 0.1 meters. What is the approximate spring constant in each spring? Given is the mass equals 0.5 kilograms and that the displacement equals 0.1 meters. And we're finding the spring constant of both springs. So first we're going to solve for the forces in the y direction. And so we're going to have the spring force minus the gravitational force, which equals 0. And then we're going to have mg equals negative kx. But the negative k is going to be the total spring constant of both springs. And so we're going to be solving for the total spring constant of both springs. So we're going to have positive total spring constant equals mass times gravity over the displacement. So after plugging in our givens, we are going to have that the total spring constant equals 49 newtons per meters. And so then, since our springs are equal, we can solve for the total spring constant as the total spring constant equals 2k. And so we're going to plug in our total spring constant, which is 49 newtons per meters, and we're going to divide it by 2, and that's going to equal the spring constant for both springs, for each individual spring. And the spring constant for each individual spring equals 24.5 newtons per meters.
Let's move on to Newton's laws of gravitation. The force of gravity is directly proportional to the mass of the objects, while the force of gravity is inversely proportional to the square of the distance between the two objects. This means that as we increase the mass and increase the distance between the two objects, the force of gravity will decrease faster than it increases because it's decreasing by more distance, because the distance is squared, than it might be increasing by mass. When we're calculating the force of gravity, it's important to always remember to include the radius of each mass, because this is included in the distance between the two masses, because it's calculated from the center of the mass. And remember that the force of gravity on each object is always equal to each other. However, the acceleration due to gravity will change depending on what the mass of the object is. Let's move on to some important formulas to know when dealing with Newton's law of gravitation. The force of gravity is equal to the universal gravitational constant times the mass of each object divided by the radius squared. The universal gravitational constant is equal to 6.67 times 10 to the negative 11 Newton meter squared divided by kilogram squared, which is an important constant to know, although it should always be given to you. Also, because we know that the force of gravity is equal to the mass times the acceleration due to gravity, we can use this to find the acceleration due to gravity using Newton's law of gravitation. And so we can see that that is equal to the universal gravitational constant times the mass of the other object divided by the radius squared. Usually the mass of the other object is the mass of the bigger object, because we're trying to find the acceleration due to gravity of the smaller object. Because we are also often looking at objects moving in orbits, we can see that due to centripetal motion, we can find the velocity of the object. And so because the mass of the object times the velocity squared divided by the radius of the orbit is equal to the universal gravitational constant times the mass of each object divided by the radius squared, we can see that the velocity is equal to the square root of the universal gravitational constant times the mass of the other object divided by the radius. Also, when we're looking at the energy of objects often in planetary motion, we can see that the gravitational potential energy is equal plus the kinetic energy is equal to 0, so the kinetic energy will be equal to the potential energy due to gravity. The potential energy due to gravity is equal to the negative universal gravitational constant times the mass of each object divided by the radius, and the kinetic energy is still 1/2 of the mass times the velocity squared.
So for our Newton's law of gravitation example, we have at the surface of a planet with radius r, a mass experiences a gravitational acceleration g. At a height of 3r above the surface of the planet, the gravitational acceleration is... Okay, so we're going to be solving for the gravitational acceleration. So we are going to use the force of gravity, the gravitational force equation, which is the gravitational constant times the first mass times the second mass over r squared. So we're going to have mass times gravity equals the gravitational force times the first mass times the second mass over r squared. And so we are going to be able to cross out the mass on the left and on the right, and we're going to be left with gravity equals the gravitational constant times the mass over r squared. And now we are going to plug in 3r plus r in the bottom of the equation, because we are evaluating this problem at three radiuses above the surface of the planet, and we also need to account for the one radius of that planet. So we are left with gravity equals the gravitational constant times the mass over 16r squared. And so now we are just going to simplify the equation, and we are left with the gravitational acceleration equals 1/16 times gravity. So for our second Newton's law of gravitation examples, we have, to launch a spaceship from Earth, we need an escape velocity of a certain escape velocity is necessary. For that same spaceship to launch from Saturn with a radius approximately 10 times that of the Earth and a mass approximately 100 times that of the Earth, what escape velocity is required? So we know that the potential gravitational energy plus kinetic energy equals 0. So we're going to set those two equal to each other, and we're going to have 1/2 mv squared equals the gravitational constant times the first mass times the second mass over radius. And we're going to be solving for the escape velocity, so we're solving for the velocity. So we have the escape velocity equals the square root of 2 times the gravitational constant times the mass over the radius. And then we are going to plug in the mass of the Earth, 100 times the mass of the Earth, and 10 times the radius of the Earth. And we're going to have that the escape velocity equals 2 times the gravitational constant times 100 times of the mass of the Earth over 10 times the radius of the Earth. And so we are going to simplify that equation, and then we are left with that the escape velocity equals the square root of 10 times the escape velocity.
Let's move on to the orbits of planets and satellites. When examining the orbits of planets and satellites, we're going to bring in a lot of the same concepts that we introduced with Newton's laws of gravitation. However, we're also going to introduce Kepler's laws. So Kepler's first law is the law of ellipses, and that states that all planets travel in ellipses. So basically, each planet in orbit will serve as one focus of the ellipse, or a planet in the sun will serve as a focus of the ellipse. Kepler's second law is the law of equal areas, and so that just states that a planet will travel an equal area of distance from an object in equal periods of time. So a line drawn from a planet orbiting the sun will sweep out in equal areas over an equal period of time. And that is, again, due to the fact that they travel in an elliptical orbit. Kepler's third law is the law of harmonies, and so that states that the planet's orbital period is proportional to the average astronomical distance cubed. So the period, it's the square of the period is equal to the cube of the radius. So t squared equals r cubed. So one cool thing we can do because of planets' elliptical orbits is we can calculate the eccentricity of the planet. So this is the how circular or flat the planet is. If the eccentricity is closer to 1, that means that it is closer to being a perfect circle, while if it's farther from 1 or closer to 0, that means that it is more oval shaped and flatter. So the eccentricity is calculated by dividing the distance between the foci by the length of the ellipse's major axis. And also some important terminology to know is perihelion and aphelion. So the perihelion is when the planet is closest to the sun, and the aphelion is when the planet is farthest from the sun. One important thing to note when looking at the orbits of planets and satellites, especially when looking at the gravitational pull between the different planets or satellites, is that some planets have a retrograde rotation, and that just means that they're spinning in the opposite direction from the other planets. One example of such a planet is Venus, and so this means that it has a negative pull because it's spinning in the opposite direction. So when you're adding together all of the gravities to calculate the force of gravity, you have to make sure to subtract the force of gravity due to the pull on Venus. Also, if you look at the chart on the right, there are, for all the different planets, it has listed their distance from the sun and their distance from the earth, in addition to the number of years it takes to travel from the sun to the different planets, in the earth to the different planets. This is just important information to know because it will be used in a lot of different problems.
So, for our orbits of planets and satellites examples, we have that Venus has an average distance from the Sun of 0.623 AU. How long does it take Venus to complete one orbit around the Sun? So, given is that the radius equals 0.623 AU, and we're trying to find the period. So, we have an equation that states that the period squared equals a radius cubed. So we are going to have the period equals the square root of 0.623 AU cubed, which gives us that the period equals 0.492 years.